Every telescope humanity has ever built is pointing at the wrong thing. Not because of poor design or limited technology or insufficient funding for the next generation of instruments. Because 95% of everything that exists in the universe produces no light, reflects no light, and absorbs no light. Every photon ever collected by every mirror ever polished has sampled the same impoverished 5% of reality. The Hubble Space Telescope, launched in April 1990 at a cost of $4.7 billion, sees 5% of the universe. The James Webb Space Telescope, the most sensitive infrared observatory ever constructed, sees 5% of the universe. The Atacama Large Millimeter Array in Chile, comprising 66 high-precision antennas, sees 5% of the universe. Every observatory on every mountaintop on every continent, every satellite ever placed in orbit, the same 5%. This is not a temporary limitation that the next generation of instruments will overcome with better mirrors. It is a structural feature of physics. The universe constructed itself so that most of its content is dark. On March 21, 2013, the European Space Agency released the most precise map of the early universe ever made. The Planck satellite had spent 4 years measuring temperature fluctuations in the cosmic microwave background. Its results were announced at a press conference in Paris, attended by cosmologists from around the world. The numbers in the Planck data were precise to fractions of a percent and confirmed what physicists had feared. Ordinary matter, atoms, protons, neutrons, electrons, everything the periodic table describes accounts for 4.9%. Dark matter, an invisible and still unidentified substance detected only through gravity, accounts for 26.8%. Dark energy, a phenomenon so poorly understood that physicists cannot agree on what it even is, accounts for 68.3%. The Planck results were not a surprise. They confirmed measurements that had been accumulating for 2 decades. But seeing the numbers published with that precision made something explicit that had previously felt abstract. We had constructed a complete inventory of the universe and discovered that we understand almost none of it. The story of how humanity discovered its own ignorance begins not with a telescope, but with a spiral galaxy. In the 1930s, Swiss astronomer Fritz Zwicky was studying the Coma Cluster, a collection of galaxies 320 million light-years away. He measured the velocities of individual galaxies within the cluster using the Doppler effect on their light. Then he calculated how much mass the cluster needed to gravitationally hold those fast-moving galaxies together. The mass he calculated from gravity was 400 times larger than the mass he could see in the visible galaxies. Zwicky concluded that the cluster must contain enormous amounts of unseen matter. He called it Dunkle Materie, dark matter. The term appeared in a scientific paper for the first time in 1933, coined by a man nobody believed. His colleagues dismissed the discrepancy as a measurement error. Zwicky was known for being difficult and abrasive. His dark matter hypothesis sat largely ignored in the literature for the next 4 decades, waiting for confirmation. The confirmation, when it finally came, arrived through the work of a woman who had been told astronomy was not for her. Vera Rubin grew up in Washington, D.C., fascinated by the stars she watched move across her bedroom window at night. She applied to Princeton University's graduate astronomy program in 1948 and received a brochure by mail in return. The brochure informed her that women were not admitted to the program. She attended Cornell and then Georgetown instead. By the 1970s, Rubin was at the Carnegie Institution measuring the rotation curves of spiral galaxies with Kent Ford. They pointed their spectrograph at the Andromeda Galaxy and measured how fast stars at different radii were orbiting. The physics was straightforward. Stars far from the galactic center should orbit more slowly, like outer planets in our solar system. The further from the concentrated central mass, the weaker gravity becomes, the slower the orbital speed should be. What Rubin and Ford observed was the opposite. Stars at the outer edges of Andromeda orbited just as fast as inner stars. The rotation curve was flat. Velocity stayed constant regardless of distance from the center, out to the galaxy's edge. This was impossible if the only mass present was the visible stars and gas that Rubin could see through her telescope. The galaxy had to be embedded in a vast, invisible halo of additional mass, extending far beyond its visible boundaries. Rubin measured dozens of other spiral galaxies over the following years and found the same flat rotation curves everywhere. Every single galaxy she examined required roughly 5 to 6 times more mass than its visible component could provide. She published her results, and this time the community could not dismiss them. The data was too clean, too consistent. By the mid-1980s, dark matter had transitioned from Zwicky's ignored hypothesis to the dominant paradigm in cosmology. The invisible scaffolding was real. The universe had a hidden skeleton that the visible matter draped itself across. What exactly dark matter is remains, as of 2025, one of the most consequential unsolved problems in all of physics. It is not ordinary matter in some dark form, not black holes, not burned-out stars, not clouds of cold hydrogen gas. Astronomers have specifically searched for and ruled out these ordinary explanations over decades of careful observation. The most compelling evidence against ordinary matter comes from a phenomenon called Big Bang nucleosynthesis. In the first 3 minutes after the Big Bang, the universe was hot and dense enough for nuclear fusion to occur. Protons and neutrons fused to form hydrogen, deuterium, helium-3, helium-4, and trace amounts of lithium. The ratios in which these light elements were produced depend sensitively on the density of ordinary baryonic matter. Measurements of primordial helium and deuterium abundances in ancient, unprocessed gas clouds constrain that density precisely. The constraint is firm. Ordinary baryonic matter can account for at most 5% of the universe's total energy content. Whatever dark matter is, it cannot be made of protons and neutrons. It is something fundamentally different in nature. The leading theoretical candidate for dark matter for 3 decades was a class of particles called WIMPs. WIMP stands for Weakly Interacting Massive Particle. A particle with mass, but essentially no non-gravitational interactions. WIMPs were theoretically appealing because supersymmetry, an extension of the standard model of particle physics, predicted them. Supersymmetry proposes that every known particle has a heavier superpartner particle that has not yet been observed. The lightest, stable supersymmetric particle, the neutralino, would have exactly the properties expected of a dark matter WIMP. It would have been produced in the right abundance in the early universe to account for the observed dark matter density. This coincidence, called the WIMP miracle, made the neutralino the most heavily hunted particle in physics history. The Large Hadron Collider at CERN began operations in 2008, partly with the expectation of producing supersymmetric particles. Underground detectors were built deep in mines around the world to catch WIMPs drifting through ordinary matter. The Lux detector in the Homestake mine in South Dakota, the Xenon experiment under Gran Sasso Mountain in Italy, the Panda X detector in the Jinping Underground Laboratory in China under 2,400 meters of rock overburden. Each of these experiments used tons of ultrapure liquid xenon cooled to cryogenic temperatures as a detection medium. The expectation was that WIMPs passing through the xenon would occasionally collide with a xenon nucleus and produce a detectable flash. After decades of operation at increasing sensitivity, none of these detectors has found a confirmed WIMP signal. The LHC has operated at energies of 13.6 trillion electron volts and found no supersymmetric particles of any kind. The parameter space where WIMPs were expected to exist has been largely excluded by the combination of null results. The WIMP miracle is looking less miraculous every year that passes without a detection in any experiment anywhere. The failure to detect WIMPs has forced the dark matter community to broaden its theoretical imagination considerably. Axions are now among the most actively pursued dark matter candidates in the experimental physics community. The axion was originally proposed in 1977 by Roberto Peccei and Helen Quinn to solve an unrelated problem in QCD. The strong force, which binds quarks inside protons and neutrons, has a theoretical problem called the strong CP problem. The standard model predicts that the strong force should violate a symmetry called CP, but experiments show it does not. Peccei and Quinn proposed a new symmetry that, when broken, produces a new particle, the axion, as a byproduct. Physicist Frank Wilczek and Steven Weinberg independently realized in 1978 that the axion could also be dark matter. Axions would be extraordinarily light, potentially 1 trillion times lighter than the electron, and produced abundantly. They interact so weakly with ordinary matter that detecting them requires extraordinarily clever and sensitive instrumentation. The ADMX experiment at the University of Washington uses a microwave cavity inside a powerful superconducting magnet. In a strong magnetic field, axions can theoretically convert into microwave photons at a specific frequency. By tuning the cavity to different frequencies, ADMX sweeps through the parameter space where axions might exist. Results published in 2018 and 2020 probed the most theoretically motivated axion mass range for the first time. No axions were found in those ranges. The search continues across multiple experiments on multiple continents. Sterile neutrinos represent another category of dark matter candidate with theoretical motivation and experimental pursuit. Ordinary neutrinos are among the lightest known particles, interacting only through the weak force and gravity. Sterile neutrinos would interact only through gravity, even more ghostly than their ordinary counterparts. X-ray observations of galaxy clusters have found a faint emission line at 3.5 keV that has no known atomic origin. This line was independently reported in 2014 by 2 separate teams analyzing data from the XMM Newton Space Telescope. One possible explanation is the decay of sterile neutrino dark matter with a mass of approximately 7 keV. The signal has been confirmed by some analyses and disputed by others, and the controversy remains unresolved. The Hitomi X-ray satellite, launched by JAXA in February 2016, was designed in part to investigate this signal precisely. It was destroyed by a malfunction just 37 days after launch before it could resolve the question definitively. Its successor, IXORISM, launched in September 2023, is now collecting the X-ray data Hitomi never could provide. Whatever dark matter is, its gravitational effects have shaped every structure we observe in the universe today. Without dark matter, galaxies would not exist in their current form. Stars would not have gathered into the structures we see. The first structures in the early universe formed when quantum fluctuations in dark matter began gravitationally collapsing. Dark matter collapsed first, forming invisible halos. Ordinary gas fell into those halos and began forming stars. Every galaxy is a luminous island at the center of a dark matter halo, many times larger than the visible galaxy itself. The Milky Way's dark matter halo extends approximately 1 million light-years from the galactic center in every direction. The visible Milky Way, the stars and gas disk we see as a band across the night sky, spans only about 100,000 light-years. We live inside a structure 10 times larger than anything we can see, embedded in an invisible gravitational cocoon. The cosmic web itself, the large-scale structure of galaxy filaments and voids that spans the observable universe, was built by dark matter before a single star had ignited, before a single atom of hydrogen had fallen into place. The luminous universe that telescopes observe is an afterthought, a thin paint applied over an invisible architectural frame. In 1998, 2 independent teams of astronomers were racing to measure the deceleration of the universe's expansion. The Supernova Cosmology Project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory, was one team. The High-Z Supernova Search Team, led by Brian Schmidt and Adam Rees, was the competing group across the Pacific. Both teams were using Type Ia supernovae as standard candles, objects of known intrinsic brightness. By measuring how bright a Type Ia supernova appears from Earth, they could calculate its distance precisely. By measuring its redshift, they could determine how fast it was receding from us as the universe expanded. Plotting distance against recession velocity would reveal whether the expansion was slowing down over time. Gravity, pulling all matter together, should have been decelerating the expansion since the Big Bang. Both teams expected to measure the rate of that deceleration to quantify how strongly gravity was winning. In late 1997 and early 1998, the results from both teams independently converged on an impossible answer. The expansion of the universe was not decelerating, it was accelerating. The universe was speeding up. Distant supernovae were fainter than expected, meaning they were farther away than a decelerating universe would predict. Something was pushing space apart with a force that was not just overcoming gravity, but growing stronger over time. Perlmutter, Schmidt, and Rees were awarded the Nobel Prize in Physics in 2011 for this discovery. The force responsible for the acceleration was given a name: dark energy. The name describes only its behavior. What dark energy actually is, its physical nature, its origin, its connection to any other known physics, remains unknown. The simplest mathematical description of dark energy is Einstein's cosmological constant, a term he added and then removed. In 1917, Einstein added the cosmological constant to his field equations to make the universe static and non-expanding. When Hubble discovered the expansion in 1929, Einstein called the cosmological constant his greatest blunder. He removed it from the equations and moved on. 70 years later, the data demanded it be put back. The cosmological constant represents a constant energy density of empty space. The vacuum itself has energy. In quantum field theory, the vacuum is not empty. It seethes with virtual particles constantly appearing and annihilating. These quantum fluctuations carry energy, and that energy should contribute to the cosmological constant. When physicists calculate the expected vacuum energy from quantum field theory and compare it to the measured value, the discrepancy is 10 to the power of 120, 1 followed by 120 zeros, the largest mismatch in the history of science. This is known as the cosmological constant problem, and it has been called the worst theoretical prediction in physics. The quantum calculation gives a vacuum energy 10 to the power of 120 times larger than the value actually driving cosmic acceleration. Something cancels the quantum vacuum energy almost perfectly, leaving only the tiny residual that observations measure. No known mechanism produces this cancellation. No extension of the standard model explains it satisfactorily. The cosmological constant problem sits at the intersection of quantum mechanics and general relativity, unsolved since 1998. Some physicists have proposed that dark energy is not a constant but a dynamic field that evolves over time. These models are called quintessence, after the fifth element of ancient philosophy beyond earth, water, fire, and air. In quintessence models, a scalar field slowly rolling down a potential energy curve drives the accelerating expansion. The field's energy density changes as the universe evolves, unlike the truly constant cosmological constant. In April 2024, the Dark Energy Spectroscopic Instrument Collaboration released its first year of survey data. DSI had measured the spectra of 6 million galaxies and quasars across 1/3 of the visible sky. The collaboration found weak but intriguing hints that the dark energy equation of state may be evolving over time. If confirmed with more data, this would rule out the cosmological constant and favor a dynamic dark energy field. The result was preliminary, sigma 2.5 significance, below the 5 sigma threshold for a discovery claim in physics. But it sent a wave of excitement through the cosmological community that persisted through 2025 as analysis continued. DESI's full 5-year survey will cover 40 million galaxies and push the significance of the measurement definitively. The philosophical implications of 95% invisible content deserve more direct confrontation than physics papers provide. Every theory, every model, every framework in physics was built from observations of the 5% we can see. General relativity describes the behavior of spacetime and gravity, calibrated on ordinary matter and light entirely. Quantum mechanics describes the behavior of particles and fields, all of them in the visible 5% of reality. The Standard Model of Particle Physics catalogs 17 fundamental particles with extraordinary precision. All 17 of those particles live in the 5%. The 95% does not contain a single particle in the Standard Model. We have built the most successful theoretical framework in the history of science from a 5% sample of reality. The question is not whether that framework is accurate. It is extraordinarily accurate within its domain. The question is what we are missing by being unable to directly observe the other 95% at all. In 2006, NASA's Chandra X-ray Observatory captured an image that became the most direct evidence for dark matter ever obtained. The Bullet Cluster is a system of 2 galaxy clusters that collided approximately 150 million years ago at high speed. When the clusters passed through each other, their hot gas, visible in X-rays, slowed down due to electromagnetic interactions. The gas from each cluster piled up near the collision center, heated by the violent impact to millions of degrees. But the galaxies in each cluster, which interact only gravitationally, passed through each other without slowing. Astronomers used gravitational lensing, the bending of background light by mass, to map where the total mass was concentrated. If dark matter exists, the dark matter halos of each cluster should have passed through each other like the galaxies did. The gravitational lensing map showed exactly this: 2 massive concentrations of invisible matter separated from the gas. The dark matter had decoupled from the ordinary matter during the collision, leaving visible gas behind in the center. This spatial separation of mass from light was impossible to explain without invoking dark matter of some non-baryonic kind. Douglas Clough, at the University of Arizona, who led the Bullet Cluster analysis, called it the most direct evidence available. The paper, published in the Astrophysical Journal Letters in 2006, was immediately recognized as a landmark observation. It did not identify what dark matter is, but it confirmed beyond reasonable doubt that something real and massive is there. The Xenon 1T experiment, operating under Gran Sasso in Italy with 3.2 tons of liquid xenon, reported an anomaly in 2020. The collaboration detected an excess of events at low energies that exceeded the expected background by a significant margin. One possible explanation was solar axions. Axions produced in the sun and converting to electrons in the detector. Another was a previously unknown magnetic moment of the neutrino, implying physics beyond the Standard Model. The excess was published in Physical Review Letters in June 2020 and generated enormous attention immediately. Follow-up analysis suggested the most likely culprit was trace tritium contamination in the xenon target material. The upgraded xenon experiment with 8.3 tons of xenon and dramatically reduced backgrounds found no such excess. The anomaly faded, but the episode illustrated how close the field perpetually operates to the threshold of discovery. Every large underground detector sits at the boundary between known physics and the 95% that has never been directly seen. Every anomalous excess of events is a potential window into the invisible majority of the universe's content. The Vera Rubin Observatory, named in honor of the astronomer whose rotation curve measurements transformed cosmology, is under construction on Cerro Pachón in Chile at an altitude of 2,715 meters above sea level. Its 8.4-meter mirror and 3.2 gigapixel camera will image the entire visible southern sky every 3 nights. Over its 10-year survey, it will catalog 20 billion galaxies and detect approximately 10 million transient events. The observatory's primary scientific driver is mapping the distribution of dark matter across cosmic time. By measuring weak gravitational lensing, the subtle distortion of galaxy shapes by intervening dark matter, the Rubin Observatory will construct the most detailed 3-dimensional map of dark matter ever assembled. It will track how the dark matter distribution evolved from the early universe to the present day. This evolution encodes information about both dark matter's physical properties and dark energy's influence over time. The Rubin Observatory began commissioning observations in 2024 and is expected to begin full survey operations in 2025. Its first year of data alone will exceed the total weak lensing measurements accumulated over the previous 2 decades. The Euclid Space Telescope, launched by the European Space Agency in July 2023, is conducting a complementary survey. From its position at the L2 Lagrange point 1.5 million kilometers from Earth, Euclid surveys the entire extragalactic sky. Its primary instrument measures the shapes of 1.5 billion galaxies with extraordinary precision over 6 years. The weak gravitational lensing signal from dark matter is typically only a 1% distortion in galaxy ellipticities. Measuring it statistically across 1.5 billion galaxies gives extraordinary sensitivity to the dark matter distribution. Euclid's first science data release in November 2023 demonstrated the instrument's capabilities with early observations. Combined with Rubin Observatory's ground-based survey and DESI's spectroscopic redshifts, Euclid will constrain the dark energy equation of state to percent-level precision, enough to distinguish between competing models firmly. The three surveys together represent the most coordinated attack on the dark universe ever mounted by human science. There is a deeper question beneath all the experimental details and theoretical candidates and null results. The question is not just what dark matter and dark energy are made of or why they have the properties they do. The question is why the universe chose these particular proportions: 5% ordinary, 27% dark matter, 68% dark energy. These numbers are not predicted by any fundamental theory from first principles. They are measured observational facts. Why not 50% ordinary matter and 50% dark matter? Why is dark energy exactly large enough to begin dominating now? Cosmologists call the second question the coincidence problem. We happen to live at the epoch when dark energy and dark matter have comparable densities, a brief cosmic moment that will not persist into the distant future. In the far future, dark energy will have diluted ordinary and dark matter to negligibility as space expands. In the far past, matter dominated and dark energy was a negligible fraction of the total energy density. We live in the transitional era, a cosmic coincidence that some physicists find deeply suspicious and others accept. The anthropic principle offers one answer. We can only observe the universe during epochs when galaxies and stars exist. Dark energy cannot be too large, or it would have prevented galaxies from forming before observers could arise. The argument is philosophically controversial and scientifically unsatisfying to most physicists who encounter it. It explains the coincidence by saying observers select for the conditions necessary for observers, circular reasoning. Most physicists believe a deeper physical explanation exists and has simply not been found yet by anyone working. The Large Hadron Collider's Run 3, which began in 2022 at 13.6 TeV, is the highest energy collider ever operated. Its extended program continues through 2025 with updated detectors and larger data samples than previous runs. The high luminosity LHC upgrade, scheduled for completion in 2029, will increase collision rates tenfold. With 10 times more data, rare processes become accessible, and parameter spaces where new physics might hide shrink. If supersymmetry exists at any energy scale accessible to colliders, the HL-LHC has a substantial chance of finding it. If it finds nothing, the community will face a genuine crisis about what physics lies beyond the standard model. The absence of new physics at the LHC has already prompted serious reconsideration of naturalness arguments in theory. Many theorists spent decades arguing that the Higgs boson mass required supersymmetric partners at LHC energies. The Higgs was discovered in 2012. The superpartners have not appeared in 12 subsequent years of searching. The theoretical arguments that predicted their discovery are being revised or abandoned across the theory community. The dark matter search is forcing a confrontation with the limits of the reasoning that has guided particle physics. In 2022, a collaboration called NanoGrav announced the first evidence for a gravitational wave background. Using an array of millisecond pulsars distributed across the galaxy as an extraordinarily precise natural detector, the collaboration measured correlated timing variations in 47 pulsars consistent with a stochastic gravitational wave background. The signal was confirmed in 2023 with higher significance and corroborated by independent pulsar timing arrays in Europe, India, China, and Australia. The most likely source of this background is the inspiral of supermassive black hole binaries across the universe. But some theorists immediately noted that a first-order phase transition in the early universe could also produce it. If dark matter is related to a new sector of physics that underwent a phase transition in the first second, gravitational waves from that transition would contribute to the background that pulsar timing arrays are measuring. The signal does not yet discriminate between these sources. The frequencies overlap, and the spectra are similar. LISA, the space-based gravitational wave detector scheduled for launch in the early 2030s, will access different frequencies. LISA can hear gravitational waves from cosmological phase transitions that pulsar timing arrays cannot resolve. If dark matter or dark energy left a gravitational wave imprint in the early universe, LISA may detect it directly. Gravitational waves travel through dark matter without scattering. They pass through dark energy without absorption. They are the first observational channel that genuinely penetrates the dark universe rather than merely inferring it. The CMB-S4 experiment will deploy 500,000 superconducting detector pixels at the South Pole and in Chile. Its primary target is the polarization of the cosmic microwave background at unprecedented sensitivity levels. The polarization pattern of the CMB carries information about neutrino masses, dark matter properties, and inflation. CMB-S4 will measure the sum of neutrino masses to a precision that may reveal whether the normal or inverted hierarchy holds. Neutrinos are the most abundant massive particles in the universe, 340 of them fill every cubic centimeter of space. Their mass contributes to the total matter density and suppresses the growth of structure on small scales in measurable ways. CMB-S4's sensitivity to structure growth will constrain the neutrino mass sum to better than 0.03 electron volts. This is precise enough to either detect or exclude most of the allowed neutrino mass parameter space entirely. If neutrinos are heavier than current upper limits suggest, CMB-S4 will find the signature in the CMB power spectrum. What would it mean to finally identify dark matter, to hold its properties in hand, and understand its nature? It would be the largest expansion of known physics since quantum mechanics was developed in the 1920s. It would mean that the standard model, the framework, that has described particle physics for 50 years, was describing only 5% of the matter content of the universe, while the other 95% operated by different rules. It would open an entirely new sector of particle physics, a dark sector with its own particles, forces, possibly interactions. Some theorists have proposed rich dark sector models, dark matter with its own dark electromagnetic force. Dark atoms, dark stars, dark chemistry, a complete parallel physics operating in the invisible majority of reality. We would not be able to see any of it, but we would know its rules and could calculate its consequences. We would understand why the universe is structured the way it is and why galaxies take the shapes they take. We would understand why we exist at all, because dark matter built the scaffolding that ordinary matter fell into. The most unsettling aspect of the dark universe is not that it exists, it is what its existence implies about knowledge. Science proceeds by observation, by measuring what is there and building theories that describe the measurements. For the entire history of physics, what is there has meant what emits or absorbs or reflects electromagnetic radiation. Every fundamental discovery, the atom, the electron, the nucleus, the quark, came through electromagnetic observation. Every spectral line, every scattering experiment, every particle track in a bubble chamber, electromagnetic signals. We have an extraordinarily complete and successful theory of the electromagnetic universe, the 5% we can see directly. The dark universe has been inferred, but never directly observed by any electromagnetic instrument ever built. Dark matter has been weighed, mapped, and tracked through its gravitational effects on visible matter for decades. But weighing something is not the same as touching it. Mapping its shadow is not the same as seeing its face. We know dark matter is there, the way a blind person knows there is a wall, by running into it repeatedly. The running in has been extraordinarily informative. It has told us where the wall is and how massive it is. But we still do not know what the wall is made of, why it is there, or whether it is actually a wall at all. There is a possibility that physicists discuss in seminar rooms but rarely in public with full directness. The possibility is that dark matter is not a particle at all, that general relativity is wrong at galactic scales. Modified Newtonian dynamics, or MOND, was proposed by Israeli physicist Mordechai Milgrom in 1983. MOND modifies the law of gravity at very low accelerations, the accelerations typical in the outer parts of galaxies. In MOND's framework, the flat rotation curves that Vera Rubin observed are a consequence of modified gravity, not dark matter. MOND makes a specific prediction. Galaxy rotation curves should correlate tightly with the distribution of visible baryons. This prediction, called the radial acceleration relation, has been confirmed observationally with striking precision. A 2016 paper by Magaw, Lely, and Schambert in Physical Review Letters showed the correlation holds across 153 galaxies. The tightness of the correlation is difficult to explain in standard dark matter models without fine-tuning. But MOND fails badly at cluster scales, the bullet cluster observation that dark matter explains naturally. And MOND has no covariant, relativistic extension that satisfactorily reproduces all cosmological observations. The debate between MOND advocates and dark matter proponents has been ongoing for 4 decades without final resolution. Most physicists favor dark matter, but the minority who favor modified gravity are not irrational or uninformed. They are pointing to a genuine tension in the data that dark matter models have not fully explained. The final resolution may require a theory that incorporates elements of both, something nobody has yet constructed. The universe that physics has revealed over the past century is radically different from the universe humans imagined. Newton's universe was filled with matter moving through empty space under the influence of gravity acting at a distance. Einstein's universe was a curved spacetime where matter and energy are different aspects of the same geometry. The quantum universe is probabilistic, non-local, and filled with fields that fluctuate even in perfect vacuum. The dark universe adds one more layer. 95% of its content is invisible, unknown, and structurally unlike anything tested. Each of these revelations required abandoning intuitions that felt self-evident to every previous generation. The intuition that what we see is what there is, that the luminous universe is the real universe, is the next to go. It is already gone, in the sense that the data has made it untenable for anyone who follows the measurements. But it has not yet been replaced by an understanding deep enough to satisfy the physicists who know what is missing. The replacement, whatever it turns out to be, will likely require the same kind of conceptual revolution that relativity and quantum mechanics each required. A fundamental rethinking of what matter, space, and energy are. The generations of physicists currently in graduate school will likely be the ones who solve this. The instruments being built now, Rubin, Euclid, DESI, CMB, S4, LISA, Xenont, ADNX, will deliver decisive data. The theoretical tools being developed now, lattice field theory, machine learning analysis, Bayesian inference, will be applied to those datasets with a sophistication not available to the previous generation of researchers. The dark universe is not a permanent mystery immune to the methods of science. It is a mystery being solved. The solution may come from an unexpected direction, a signal in a detector nobody was specifically watching for. It may come from a theorist who notices a connection between two apparently unrelated anomalies in the existing data. It may come from an observation of a phenomenon nobody predicted and nobody has yet seen anywhere in the sky. The history of physics is full of solutions that arrived through doors nobody had thought to build or knock on. The 95% will not remain invisible forever. The universe left traces of itself in the 5% we can see. Every galaxy rotation curve is a trace. Every lensing map is a trace. Every CMB power spectrum is a trace. We are reading the 95% through the distortions it causes in the 5%, and we are getting very good at reading. The golden age of dark universe science is not behind us. It is precisely and unambiguously ahead of us. Every null result from every WIMP detector has tightened the constraints and focused the theoretical landscape. Every anomaly, the 3.5 keV line, the XENON1TXS, the DESI dark energy hint, is a possible first crack. Every gravitational lensing map is another piece of evidence about where the invisible scaffolding sits. Every pulsar timing measurement is a potential gravitational wave signal from a phase transition in the dark sector. The instruments are more sensitive than ever. The theoretical models are more specific than ever. The data is coming. Somewhere in the parameter space that remains unexplored, the dark universe is waiting to be found by name. The numbers themselves deserve one final pass, stated plainly, without softening, without metaphor to cushion them. Of all the energy and matter in the observable universe, 4.9% is the ordinary atoms that make up everything we have ever touched. Every mountain, every ocean, every star, every nebula, every planet, every bacterium, every human being, 4.9%. Every particle accelerator ever built has studied particles from this 4.9%. Every chemistry textbook describes this 4.9%. Every telescope ever constructed has captured photons emitted, reflected, or scattered by objects in this 4.9%. The remaining 95.1% has never been directly detected by any instrument, in any experiment, on any continent, in any era. This is not a matter of interpretation or theoretical preference or which cosmological model one finds most compelling. It is the direct result of measuring the universe's geometry, its expansion history, and its structure simultaneously. Three independent lines of evidence, supernova distances, CMB fluctuations, and large-scale structure surveys, all converge on the same proportions when analyzed with the tools of modern cosmological inference. The convergence is not coincidental. It reflects a genuine feature of reality that every measurement confirms. Consider what it means for the concept of a complete physical theory to live in a universe constructed this way. The standard model of particle physics is the most precisely tested theory in the history of human thought. Its predictions match experiments to 12 decimal places in some cases, a precision without precedent in science. It describes every known particle and every known force except gravity with extraordinary completeness and accuracy. And it describes exactly 4.9% of what the universe actually contains. The other 95.1% is outside its scope entirely. General relativity, Einstein's theory of gravity, describes the geometry of space-time with equal extraordinary precision. It predicted black holes, gravitational waves, the expansion of the universe, and the bending of light by mass. Every prediction has been confirmed. It is arguably the most beautiful physical theory ever constructed by a human mind. And general relativity, when applied to the full universe, requires dark matter and dark energy to fit the observations. The theory that describes gravity, the force that governs the large-scale structure of the cosmos, demands the existence of 95.1% invisible content that no part of the theory itself can explain or describe. The two most successful theories in physics are each in their own way confessing to the same ignorance. They are saying, we work, we fit every observation we have ever been tested against, and we are radically incomplete. This incompleteness is not a crisis in the sense of something going wrong with the scientific project. It is the opposite. It is the scientific project working exactly as it is supposed to work at its best. Science does not claim to have finished. It claims to be getting closer, one measurement at a time. The discovery that 95% of the universe is dark is not a failure of science. It is one of science's greatest achievements. It required building instruments of extraordinary precision, developing statistical methods of great sophistication, and having the intellectual honesty to follow the data to a conclusion that humbled everyone who calculated it. The scientists who discovered the accelerating expansion did not want to find what they found in 1998. Perlmutter's team and Schmidt's team both initially suspected their own data before the universe accelerating its expansion implied an energy source nobody had observed and nobody could explain. Accepting that result required the courage to report something that made the universe fundamentally more mysterious. That courage, the willingness to publish a result that raises more questions than it answers, is what science is. The dark universe is not an embarrassment. It is an invitation. It is the universe telling us we are not done yet. Thank you for following this journey through the 95% of reality that every telescope in history has never seen. If this changed how you think about what exists, subscribe and stay for every invisible thing we are learning to read. Your willingness to look at what cannot be seen is exactly the quality that eventually makes the invisible visible.